changes in atmospheric chemistry, and the role that has in changes in temperature. And then I'll bring it a little bit closer to home in terms of thinking about some of the regional impacts as it relates to climate change, especially as it relates to water, which is one of my driving interests in terms of water resources, especially here in the West. So let's start on the geologic timescale, and here I know I'm cheating a little bit. Some of my geology colleagues give me a hard time. 70 million years, okay? It's a long time scale for those of us that work in modern time periods. Here I'm showing a graphic that is compiled from a series of data sets from Giff Miller at UC Boulder that was part of a compilation analysis looking at oxygen isotopes from benthic or deep water foraminifera, these really cool little creatures that hang out in the bottom portions of the ocean, and they uptake oxygen is part of their shells, and their oxygen signatures tell us something about temperature in the past. So the time frame on the x-axis here is tens of millions of years, going back to 70 million years on the left side of the x-axis. And this vertical axis is actually an indication of oxygen isotope levels, but think of it here as a gauge of temperature. Actually, cooler temperatures are down here towards the origin. Warmer temperatures are up here towards the top. One thing that I like to point out in terms of thinking about timescales on the order of tens of millions of years is the process or the forcing that is going on that impacts climate. In this case, we're actually focusing on the issue of tectonics. So there are three main shifts that occur in this graphic that I'm going to point out between about 35 and 55 million years ago, this overall decline that you see, that's when Antarctica makes it to its current location at the South Pole and ice starts to build up. That actually leads to an overall cooling of our planet. And I'll explain why in just a moment. There's another inflection point that occurs about 15 million years ago, and that's associated with the uplift of the Himalayan mountains. And then the third tectonic component as it relates to climate change on this time scale is right down here at the edge of this graphic about 2.5 million years ago, and that's the closing of the Isthmus of Panama. And what that did is that actually changed ocean circulation, which led to a change in overall global climate. So if we look at this graphic, the overall trend is a downward trend indicating that climate's cooling on our planet. If you look at it from the last 70 million years, and I've got this sort of rhetorical question down here that I often ask my students, does the cooling over the last 70 million years negate the recent warming trends that we've seen over the last 150 years? This is not a test, by the way. You guys don't have to answer this question. That's why I sort of pose it as a rhetorical question. The answer is no. But time scale matters, and we're going to get to this issue of recent warming here in a little bit. In terms of thinking about the role of tectonics as it relates to climate change, there are kind of a couple of components. One of the major components has to do with orography or uplift and the weathering of mountains. So this figure, which was created by Bill Rudiman, a really great geologist, he created a series of general circulation models. On the left-hand side is an example of sea level pressure. That's what SLP stands for, sea level pressure, with no mountains. And you can see in the light gray, this is the outline in the front part of this graphic. This is North America. Looks real North American-y, of course, because it's a coarse gridded scale. Now, without any mountains, and this block, darker block represents where the Rocky Mountains eventually will be, right? Without mountains, without that north-south trending mountains, general airflow seems to have a very sort of circumpolar pattern to it. Add mountains, which is what the right-hand figure is showing us, with added north-south trending Rocky Mountains, and he also added the Himalayas over here, which are more east-west trending, but add that north-south trending mountains, and that causes the flow of air in the atmosphere to dip and move, essentially helping to create some of the perturbations that we see in the jet stream even today. Right? We think of the jet stream as or I like to talk about the jet stream as this kind of noodly part of the atmosphere, right? The atmosphere is a fluid mass, and just like on a river, any rock that it encounters, it has to move around or over. And that's what this north-south trending mountain range, or the presence of this north-south trending mountain range, helped to do in terms of climate. Another aspect of how mountain building has helped to impact our planet's climate is through the weathering process. And this is another perspective in terms of thinking about a positive feedback loop where uplift occurs that leads to global cooling, which leads to an increase in ice. That increase in ice leads to an increase in rock fragmentation and weathering, which decreases CO2. Right when there's weathering that occurs, CO2 is drawn out of the atmosphere in the formation of carbonic acid and the weathering process. And whenever CO2 is taken out of the atmosphere becomes cooler. So this is another sort of process, another mechanism for which, on the long time scales of tectonics, climate can be impacted. So we've got our 70 million year time scale, and thinking about the Cenozoic and the overall cooling that's occurred in the Cenozoic is real and measurable. Within that last 2.5 million period was our last big tectonic event of the closing of the Isthmus of Panama. And that's what this bottom graphic is showing the last 5 million years, or it's really blowing this up so you can see a little bit more detail. About 2.5 million years ago, you can see the frequency of climate becomes considerably greater. And that's a function of that closing of the Isthmus of Panama. So 5 million years ago, that isthmus is an isthmus, it's open, and ocean waters in the tropics between the Atlantic and the Pacific are mixing. But as that isthmus closes up, present day, over the last 2.5 million years, essentially what happens is that cuts off the flow of temperature, ocean waters, and ocean circulation between these two basins, and it sets up the present day Gulf Stream and our conditions that we have for our trade winds. So that last little push that occurred 2.5 million years ago really set the stage for this Gulf Stream that we will come back to when we're thinking about present day climate. One way that we're going to do that is by linking that change in ocean circulation with something that we refer to as the thermal haline circulation or the ocean conveyor belt. Newer publications are referring to this as the Atlantic meridional overturning circulation. It's far more complex. Let's keep it simple here for our purposes. The red arrows indicate warm surface water. The blue arrows indicate cool, deep ocean water. So you can see that these warm ocean waters move up towards the north part of the Atlantic, and then they start to sink. The reason they sink is because of temperature, thermo, and salinity, haline. So it's the cold and the saltiness in the north part of the Atlantic that actually sinks and causes that water to be pulled up. Instead of mixing with the ocean and the Pacific, because the isthmus is now closed, that water comes up here and makes northwestern part of Europe warm. Certainly warm than its comparable latitudes in, say, in parts of Alaska. Now I want to pivot here to a different time scale. So we've dealt with geologic time scale in terms of the last 70 million years. Now the next scale down in time from tens of millions and millions of years is hundreds of thousands of years. So here we're looking at changes in Earth's orbit, and there are three major components to Earth's orbit. There is the shape of the Earth's orbit, which we refer to as the eccentricity. Sometimes the Earth's orbit is mostly elliptical, sometimes it's almost circular. It takes about 100,000 years for that process to occur very, very slowly. Okay? The reason those changes in the Earth's orbit occur is because of the gravitational pull of the sun and the gravitational pull of the larger outer planets. They impact these three components of Earth's orbital variability. So the eccentricity is the first one with the longest time period. Then there's the obliquity of the axis, or the tilt of the Earth on its axis, and that changes from about 21.5 to 24.5. Currently we're tilted at about 23.5 degrees. That's what we refer to as the tropics of Cancer and Capricorn in the north and southern hemisphere respectively. right? That tilt changes over a periodicity of about 41,000 years. And then there's a third component, which we refer to as the precession of the equinoxes. Think of this as axial wobble, right? When a top circulates and moves around, it also has a secondary wobble component. The Earth is like a top, a celestial top in a way, and it both spins on its axis, but it also has a wobble in terms of its tilt. That axial wobble determines when we have our equinoxes, right? So today, December 21st, we are physically closest to the sun. But it happens to be cool in the northern hemisphere because the northern hemisphere is tilted away from the sun on December 21st, right? But 11,000 years ago, June 21st, we were both pointed towards the sun and also closest to the sun. So 11,000 years ago, it was actually pretty warm. And that meant very different climate. It meant for very different vegetation types and things like that, which we'll talk about here in a moment. In terms of thinking about this particular time scale, which we often refer to as Milankovitch cyclicity or the pacemaker to the ice ages, these are the control, this is the process, these changes in the Earth's orbit, this is the process that really sets up whether we have ice on our landscape in the form of large glaciers or whether we're in an interglacial from a natural perspective, okay? So here, now our time frame on this x-axis is 800,000 years. And each one of these major tick marks is 100,000 years, and the smaller tick marks are less. You can actually see in this reconstruction of ice volume that we've got these pockets of time that are like 100,000 years long, and then smaller scale variability that is associated with these three time components, 100,000, 41,000, and 23,000. 23,000 years happens to be pretty important because 23,000 years ago was our last glacial maximum, or our last ice age. This is an animation. This is what happens in graduate school when your graduate advisor says, oh, hey, you should digitize these maps. And then you digitize and think, what is happening here? And then we put together those digitized maps in the form of an animation, which actually ended up being kind of cool. Because when we look 21,000 years ago, this big blue blob is the Laurentide Ice Sheet. You can also see that Florida looks all big and fat because sea level was considerably lower because there was a bunch of water locked up on the land in ice. In other words, when ice melts on the land, it goes into the ocean and sea level rises. So you can see Baja, California down here, and you can see Florida get skinnier and skinnier through time as a result of sea level rise because this ice sheet is melting as well as other ice sheets that are on the continent of Eurasia or alpine glaciers that are elsewhere on the planet. At its greatest extent, the Laurentide Ice Sheet extended from the Pacific Northwest coast to the East Coast, about as far south as present-day Chicago, and it was about 2.5 kilometers thick at its thickest, which sort of makes it like a rock in the stream of the atmosphere. So that Laurentide ice sheet presented an interesting shift in terms of atmospheric circulation. In comes Bill Rudiman again, and actually this is from a paper, a very seminal paper in science, COMAP, 1988. This is Cooperative Holocene Mapping Project. Somewhere around the 1980s, a bunch of people got together and said, hey, you're a scientist, you've got data about pollen, you've got data from tree rings, you've got data from pack rat middens and lake levels, and they all got together and they mapped out their data together collectively to visualize what was happening and to try to recreate what atmospheric circulation may have been like during the last glacial maximum. So again, you can see that North America is simplified in this general circulation model grid view. What's interesting about this in terms of modern day winters is we have this dip that occurs within the jet stream. That changes from day to day and week to week, but on average, right, the jet stream is forced over the Rocky Mountains and plunges down into the Midwest. 23,000 years ago, when there was a big ice sheet, that was not the case. 23,000 years ago, with that 2.5 kilometers of that ice sheet spanning from the Pacific Northwest to the East Coast, it essentially blocked the jet stream and forced the jet stream to the south. So I've seen plenty of climate data, pollen data, and pack rat midden data from where I grew up in southern Arizona and Tucson, and 23,000 years ago there were pine trees and not saguaro cactuses because it was considerably wetter. You know, all these great, fantastic lakes in the Great Basin filled up because they got lots of precipitation 23,000 years ago as a result of the shift in the jet stream. When that ice sheet melted, the jet stream shifted back up north. Here's what's interesting to me about this shifting jet stream and present day climate in the West. One word that I will note here that's important is this word variability. And I'm sure everybody in this room can appreciate the notion of variability. I've heard from a number of people today just around the room about how much snow you all have gotten this year, right? That may not be the case next year. In fact, it wasn't so long ago that 2011 was one of our wettest years on record here in Wyoming, and 2012 was our absolute single driest year in Wyoming. We have a high degree of variability here in the interior Intermountain West. Part of that has to do with the mountains and with the jet stream, but we can use this as an analogy. 23,000 years ago, when the jet stream was shifted to the south, the Intermountain West was at the northern extent of the southerly shifted jet stream. In other words, the jet stream's moving, and there's a high degree of variability in the Rocky Mountains. Today, the interior Intermountain West is at the southern extent of the northerly shifted jet stream, meaning we get a lot of variability because the jet stream moves a lot. I love to embrace variability. It tortures my students because they want to know an answer. They want to know specifically what's going to happen. And I tell them to embrace some variability because we live in a variable climate for a number of different reasons. Now, let's pivot towards the present. We've dealt with tens of millions of years from geologic and tectonic processes, hundreds of thousands and tens of thousands of years in terms of orbital variability. Now we're going to talk about modern day climate and how it varies, right? That's the down and the ups, but also the trends. What we're looking at here is January through March, and it happens to be in particular this January through March. This January through March compared to 1880 to present. The zero line on all of these graphics represent a long-term mean from 1980 to 2001. Anything above that zero line is warmer than that long-term average. Anything below that line represents cooler than that average period. The top is showing global temperatures, the middle is showing northern hemisphere, and the bottom is showing southern hemisphere. And I will point out that the southern hemisphere, the increase in temperature, or the changes in temperature, seem smaller. And that's because there's so much ocean in the southern hemisphere. And anytime you have a lot of water bodies, it takes longer for those water bodies to warm up or cool off. So you're going to see a sort of a milder response in the southern hemisphere than you would, say, for example, in the northern hemisphere. So you can see that temperatures have both been cooler and they varied. And then there appears to be this trend. That trend is real, as it turns out. And it's actually important in terms of thinking about changes in temperature over each individual month, January to December on this x-axis, and the y-axis represents difference in temperature from the 20th century average. What's being plotted here, first of all in black, these 3 months, that's January, February, and March of 2019. It's being compared to the 10 warmest years on record since 1880. So it's comparing the 10 warmest years from this graphic. The 10 warmest years, well, they happen to be 1989, 2009, 5, 13, 10, 14. You see where we're going here, right? Most of these warmest years on record have been in the last 10 to 15 years. We are on track for 2019. So far this year, we're in the top 3 of warmest years. As we move through the seasonal cycle, as we head towards summer and again towards the end of the year here in 2019, I'm pretty sure we're still going to be somewhere in this top 10 in terms of this particular year. The planet has to cool off a whole lot for us to drop out of this graphic here. And the reason that is because instead of tectonics being the driving force, instead of orbital variability being the driving force, now humans are the driving force. And we have literally changed the chemistry of our atmosphere. Much like chemistry gets changed in the atmosphere from a tectonic perspective, but that's occurring over tens of thousands to tens of millions of years. And what we've seen over the last 150 years is a change in atmospheric chemistry that outpaces what we have seen naturally occurring. And this is where it gets really interesting. We're looking at just from 1959 to present in terms of concentrations of CO2. These are measured concentrations around the world. This particular graphic is from Scripps Institute of Oceanography from Mauna Loa Observatory, which is where these measurements began in the World Geophysical Year of 1960, when Charles David Keeling started measuring carbon dioxide in the atmosphere. At first, when he was measuring, he noticed what he expected, the seasonal rise and fall. That's the small scale changes, right? It's sort of the planet breathing in and photosynthesizing and then exhaling and not photosynthesizing during northern hemisphere winter. But he noticed each year the concentration of CO2 values became greater and greater and greater, and at first he thought his machinery was messed up. Turns out his machinery was dead on, and it was measuring an ever-increasing rate of CO2 that ends up looking like an exponential increase, because it is. We've gone from pre-industrial levels of 280 parts per million to now, as of April 2019, 413 parts per million. It's a small amount, right? It's measured in parts per million, but it has a huge impact on the temperature knob of our planet. So we're going to look at a variety of timescales here. I'm going to start off with 1,000, go back a little bit in hundreds of thousands, and get us closer to present. So I'm going to yo-yo you in time, so hang on, okay? Here we've got 1,000 years down here on the bottom. Present's over here on the right. 1,000 years ago is closer towards my side of the slide. The bottom or front part of this graphic is measuring carbon emissions. Okay, and reduction in carbon sinks. The tan represents land use change. So you can start to see the tan increasing when we start to have large-scale changes on our planet of deforestation, right? This is an indication chemically of changing the surface of our planet to more agrable land, more agriculture, clearing forests and things like that. The blue part of this front curve represents fossil fuels, which we don't start to see until the Industrial Revolution, where we are literally taking material, carbon, that's in some sort of reservoir under the ground in coal, as a liquid or as a gas, and when we combust it, it is then liberated. Because as I tell my students, the first law of thermodynamics is stuff doesn't disappear. Okay, which is really important here. As a result, the middle part of this graphic is showing CO2 concentrations as it relates to carbon emissions, and they vary, but you can see that they really start to increase when both land use change and the use of fossil fuels start to increase exponentially. And our temperature change in the back over the last 1,000 years again fluctuates, but overall also starts to mirror that process of what's going on in terms of the changes in the chemistry of our Earth's atmosphere. Now, how do we know that the changes in the chemistry of the Earth's atmosphere have changed so drastically. And we can compare this to different timescales. That's why timescales matter, and that's why it's so important. On this graphic, 0 is near the origin, and 700,000 years is over here on the right-hand side. Every major tick mark is 100,000 years. You can see that repeatable pattern of the Earth's orbital variability because we're looking at that time scale. Each one of the individual smaller tick marks is 10,000 years. These are CO2 concentrations as identified from ice cores in Antarctica. This is from the European Project for Ice Coring in Antarctica. And they've gone back 700,000 years. They've actually gone back 1 million years now. And it doesn't look much different than what I'm showing you here. What's interesting is that from a glacial period, which is this last glacial maximum, roughly 24,000 years ago, to pre-industrial levels, we went from 180 parts per million to 280 parts per million based on those measurements from those ice cores. It took 20,000 years to go 100 parts per million increase in atmospheric CO2. This is how amazing humans are. We've gone from 280 to now we are literally, officially as of this year, we are off this chart in terms of 413 parts per million in 2019. So we have gone from pre-industrial levels of 280 to more than that in 169 years. That's pretty awesome. That is literally changing the chemistry of our atmosphere at a rate that surpasses natural variability. Now, how we understand that we are changing the chemistry of our atmosphere and the implications it has in terms of climate has to do quite literally simply with atmospheric physics and atmospheric chemistry. So I'm giving you a crash course in atmospheric chemistry and atmospheric physics in 3.5 minutes or less. You ready for this? Okay. It has to do with inputs and outputs. Step 1. Input, solar energy from the sun, comes into our planet and it experiences a variety of different pathways. Sometimes it gets bounced back up to space because of albedo or reflectivity of really bright clouds or really reflective surface. Those of you that are skiers can appreciate this, right? But a good majority of that incoming solar radiation makes it to the surface and is absorbed by the surface. The Earth, because it is cooler than the sun, emits energy at a longer wavelength, because the cooler the body, the longer the wavelength. The warmer the body, the shorter the wavelength, right? So the sun has really short wavelengths, makes it through the atmosphere, is absorbed by the surface, and then the Earth radiates it as long wave radiation. The gases in our atmosphere, which naturally occur and presently occur at unnatural amounts because of human activity, we call them greenhouse gases because they absorb long wave radiation and they radiate it back to the surface. Here's how it works. In this graphic, we're looking at wavelengths on the x-axis. Wavelengths are small towards my side of the graphic. Wavelengths get longer towards the right-hand side of the x-axis, okay? The red curve up here, that's the wavelength of energy that's emitted by the sun. Note, it's on the short side of wavelength spectrum. The blue curve, because the Earth is cooler than the sun, the Earth emits infrared or long wave radiation. Most of the gases in our atmosphere are invisible to incoming shortwave radiation. But most of those gases are actually opaque or not invisible to long wave radiation. So anywhere in these horizontal graphs where you see nitrous oxide or methane or carbon dioxide or water vapor, anywhere where it's shaded in, that's a wavelength that gas effectively absorbs at that wavelength. Note, carbon dioxide does not absorb at the short wavelength. So incoming solar radiation is not affected by greenhouse gases. It's outgoing long wave radiation or this energy that is absorbed at the surface and then re-radiated back out. Okay, that took less than 3 minutes. There's your atmospheric chemistry and physics. What's cool about this is that each of these gases, CO2, carbon dioxide, CH4, methane, N2O, nitrous oxides, or NOxes, that mostly have a positive radiative forcing when it comes to the atmosphere. That's why they're called greenhouse gases. Anything here that it has a positive radiative forcing, it warms the planet. Anything to the left of the zero means it cools the planet. So you can see here, like aerosols, like minerals and dust and let's see, salt from the ocean, organic carbon and things like that. Those typically have a cooling effect, right? Like volcanic eruptions will have a tendency to block incoming solar radiation and cool the planet temporarily. But these other gases, they largely pile up. So overall, since 1950, there's been a half tick of increased radiative forcing. From 1980, triple that. 2011, quadruple that. So more and more material going into the atmosphere from some reservoir, solid, liquid, or vapor. Otherwise, once it's combusted, moves into the atmosphere and contributes to the total radiative forcings that we've seen since the Industrial Revolution. Now note, these bars down here get longer and longer. There's a relationship as it occurs in terms of temperature. This is temperature, overall temperature, annual mean and smooth time series from thermometers. Global mean temperature from the late 1800s to roughly present. If you average out this temperature, the red line represents the last 150 plus years where we've seen a rate of change where temperatures are increasing. But note each of the subsequent slopes of the colors following, the purple, the orange, the yellow, are steeper and steeper and steeper. As we move closer to present, we are building up more and more of these gases and their enhanced radiative forcings leading to more rapidly increasing temperatures. So it's not just that temperatures are warming, they're warming at a faster and faster rate, moving closer to present and as we move towards the future. Now, one question is, how do we know that it's really humans? It's been a point of discussion. I mean, I thought I kind of dispensed with that in terms of thinking about the physics and the chemistry of it, but let's look at some other pieces of the puzzle here, just to bring home this message. One way to identify whether we're just talking about natural processes, because I've already identified that climate changes because of a variety of different processes. Tectonic, orbital variation, in this case now we're adding humans to the picture. If we only think about natural forcings, that is, changes in the sun's strength or volcanic eruptions that have a tendency to cool down the planet, you can see El Chichon and Pinatubo over here on the far right-hand side of this bottom curve and the top curve as well, right? Those are pulling temperatures down. The black line on both of these graphics represents reconstructed temperatures from thermometers. The colored lines represent models reconstructing those same temperatures. So the notion here is if we can model data that recreates what we know has happened in the recent past, then maybe we can use that same model to look forward in terms of what may be happening in the future. So the only way that we can reconstruct past temperatures accurately is if we include natural forcings of the sun and volcanoes and greenhouse gases and sulfate aerosols. Because if we only look at natural forcings, which is this curve down here, the blue curve down here, we cannot reconstruct those temperatures. Only by including greenhouse gases and sulfate aerosols. The greenhouse gases help to warm the planet, sulfate aerosols cool the planet a little bit, but this red line tracks the black line pretty darn well. If you're not convinced, there's more. And this is another piece of that puzzle. Looking at daytime and nighttime temperature ranges, or what's referred to as the diurnal temperature range is another way that it's discussed. Here we're looking at temperature anomalies, so 0 is some normal condition and positive is warmer, negative is cooler. from 1950 to present. So if warming is a function of greenhouse gases as opposed to the sun, then nighttime temperatures should increase faster than daytime temperatures. In other words, the diurnal temperature range would start to go down, right? Because the sun's not out at night, but greenhouse gases still exist in the atmosphere at night. And they're still absorbing long-wave radiation at night. So sure enough, we have seen minimum nighttime temperatures go up. And the diurnal temperature range has gone down. In other words, the difference between daytime and nighttime temperature has decreased. One argument that is put forth is maybe it's the sun. Maybe the sun's variability in terms of solar activity, when the sun's really active or when the sun's not so active, maybe that's causing some of the warming that we see. So if we look at solar energy output, sun's active, sun's not so active, active, not active, it has this 11 to 22-year cycle to it. If we were to put an average line through that graphic on the bottom, through this red graphic here, it would look horizontal. But yet, our global average temperatures are increasing. So, it's not solar activity. Another point that's often put forth is, what if it's urbanization? Now, granted, urbanization is not a big deal here in Wyoming. But urbanization has been a big deal elsewhere in the world. And the notion is that we have changed landscapes where we've removed water from the surface and we've removed vegetation from the surface and we've put concrete and asphalt and really changed the surface. And as a result, cities have a tendency to be, on average, warmer, right? But if you compare all data and compare it to data minus stations that are near the cities, the difference is this purple line. So, the overall temperature changes that we are seeing presently are not a function of changes in solar variability. They're not a function of urbanization. They are a function of changes in the chemistry of the Earth's atmosphere as a result of human activity. This graphic, going back 1,000 years, shows us that temperature fluctuates. This modern portion right here is thermometer measured temperatures, and you can see the increase. And to the right, looking forward from 2000 to 2100, or as I like to say, the next 80 years now, we're committed to future warming. It's not going to get cooler. There will be bouts of cold. There will be extremes. Those exist no matter what. Remember, variability is a word that we should embrace, but overall temperature trends, they're unidirectional moving forward. Overall, in terms of temperature on our planet, changes in temperature likely to see between 1.3 and 5.5 degrees Celsius. Some parts of Wyoming have already seen 2.5 degrees Celsius increase in temperatures. So we're already outpacing the next 80 years here in Wyoming, right? All right, now I want to pivot to what temperature means to one of our most valuable resources, water, which requires me to take a sip. You can see on this graphic the 7 driest states in the US. Can you imagine a national average of precipitation of 36.6 inches? It's like mind-blowing to me. I grew up in Arizona, number 4. I live in Wyoming now, woohoo, number 3, in terms of overall annual precipitation, right? This is average annual precipitation. For Wyoming, it's really different than some other states because a majority of our land area above 10,000 feet is heavily snow dominated. You guys are here, okay? In that beautiful, heavily snow dominated environment. But look at the rest of the state. That's why we're number 3 in terms of precipitation, because those lower elevations don't get as much. It turns out that what falls in the mountains as snowpack is very important, not just for our water resources, but for all those thirsty people downstream. We have a very unique situation here in Wyoming in terms of our major river basins. The Wind River Range is a unique place that has headwaters to 3 of the major river basins in this country. It has headwaters to the Missouri-Mississippi River. It has headwaters to the Snake and Columbia River, right here in our own backyard. It has headwaters to the Green and the Colorado. Right here at Lake of the Woods, which is right on the Continental Divide. I love to show this figure because, in my opinion, this is one of the most beautiful places on our planet. In comparison, as a source, I think about this as a source. And then these people take that beautiful snowpack. Now, granted, I understand that much of the water in the fountain in the Bellagio is using reclaimed water, so I'm not going to be on their case too much, but when you're in Las Vegas, some people are just overwhelmed by certain aspects of Las Vegas, like maybe the gambling or the drinking or whatever. I'm amazed at the water. I can't help myself every time. What are you doing to my water? This is our supply. This is part of our demand. We are required in Wyoming, as a headwater state, as an upper basin state to the Colorado River, to deliver water to these thirsty people in Vegas and Phoenix and a little bit down in Tucson, but also to the folks over here in one of the driest parts of the country where they get less than 3 inches of rain per year in the Imperial Valley, where they grow, thankfully, 50% of our fruits and vegetables. Courtesy of this beautiful water right here, right? So there's a supply and demand issue. How does this relate to climate? In terms of thinking about climate change, we're looking from the 1900s forward into 2100. Each of the colors on this graphic represents a different climate model. The one thing that they are all in agreement is the direction of temperature changes. Temperature is increasing already and will continue to increase moving forward. They are not in agreement in terms of precipitation because, as it turns out, temperature doesn't cause precipitation. But temperature does impact water resources, which is where I'm going to go with this. Your 3 options in the future for the upper Colorado River Basin is it could be wetter, it could be the same, or it could be drier. Totally easy from a water resource perspective. Water resource managers hate it when I say that. But in a way, you've already minimized. You've got 3 options. It's going to be wetter, the same, or drier. Just add to that population increase. So this is a great figure that I always like to add this potential quote from Mark Twain, you know, whiskey's for drinking, water's for fighting over, okay? This is where we're headed in the future in terms of our demand because of population increase in red and our estimated flows from the upper basins in gray. This inflection point is like day after tomorrow almost. It's like 2027 or 2030. It's only 10 years from now, 11 years from now. I'm telling you today that there are a ton of people in Colorado and Arizona and California that are like, woohoo, thanks for the snow. That all of our snow totals in a majority of the West, the interior West, are at or above normal. The reason I show this as graphic is because the notion of long-term variability is important for us to contextualize present-day changes. And one of the ways that we get at this is through geophysical research and also through sediment cores. Brian Schumann, who I think has talked to this group before, this is Brian Schumann and I doing some research. You know, it's tough working out in these areas. I particularly love this lower right graphic. Here's Brian with one of his graduate students. There's $60,000 ground penetrating radar in a $20 Walmart inner tube. Okay? It is real science that is being done. What's amazing about this is Brian can identify when shorelines were lower than present, which is one piece of information. Then he picks up the phone and he calls me and he says, how does it get dry in this location? Because he only has one part of the story, and he wants to identify some of the conditions that may cause that. Now certainly, hey, it gets dry because there's less precipitation. I get into some more detail with that, which I'm happy to talk to anybody about, atmospheric circulation and controls of moisture and things like that. But for now, I want to shift to my neck of the woods over here in southeast Wyoming, in this little basin, which we call the Upper Platte River Basin. It's not as complicated as the Colorado. The Platte River Basin's 100% allocated, but it's allocated by percentage. So it's a little bit easier, and it's allocated between these 3 states, Colorado, Wyoming, and Nebraska, and there are no tribal units involved in this water allocation, so it's a little bit more straightforward. But I'm going to show you how changes in temperature impact water availability in this particular basin. From the early 1900s to present, we have seen an increase in temperature annually and every season within those years. You can see that there's a fair amount of variability in terms of temperature, but the overall trend is an increase, and it is statistically significant. What's amazing about this is over this record of period, temperatures have increased 1.44 degrees C since 1916, which far surpasses previous identification of increases in temperature. Here's the really amazing part. If we just look at spring, which is the black line, spring temperatures have the greatest rate of change, 2.21 degrees C. So in this part of Wyoming, in the southeast corner of Wyoming, we're surpassing global average temperature predictions. That's how fast it's warming up. It's warming up so fast, it's 1.5 times the rate of the annual increase of temperatures. Why does spring matter? That's when the snow melts. And this is how temperature is relevant from a water resource perspective. If we look at precipitation, you can really see how precipitation anomalies vary quite a bit. There is an overall decline of winter precipitation. So now we have a combination of less winter precipitation and warmer than normal springtime temperatures. Put that together in terms of when runoff is occurring. And you have a very interesting situation. At the North Gate, which is a USGS stream gauge, above any impoundments, there is a decline in the timing of runoff. We have identified that for every degree C in March, April, and May temperature, you see almost 5 days earlier onset of spring snowmelt. In other words, for this time period, over almost 2.5 degrees C increase, spring is coming almost 11 to 15 days earlier, which is like a half of a month. And for the 3rd driest state in the country, we need that water. For this part of the state, they need it for those folks over in Nebraska, you know, growing things important for our economy and stuff like that. We also use this water for energy extraction as well. If we have less water early in the spring, we have less water late in the growing season. Which brings me to a final point in terms of where we're headed in the future. This is an interesting study where some folks looked at calculated Palmer Drought Severity Index. It's a measure of droughtiness, okay? Red means real drought, green and blue mean less drought. What these scientists did in their analysis is they looked at historical dry periods. The 1950s drought up here in the upper left corner, the early 2000s drought in the lower left corner. What's really interesting about this particular study is they identified increases in temperature. Note, this increase in temperature, no significant change in precipitation, plus 1.4 degrees increase in temperature. They're projecting that to occur 2006 to 2030 in the southeast corner of Wyoming. We've already surpassed that. With no changes in precipitation, this is what we would anticipate a warmer climate meaning in terms of drought conditions. With an increase of 2.8 degrees C and no significant changes in precipitation, this is what we're looking at in the lower right from 2035 to 2060. So even without changes in precipitation, we can put a pin in precipitation, and we can just think about the increase in temperature and what it means for early spring runoff, early snowmelt, and what it means for late season flow. And we're looking at more drought-like conditions moving forward. What I've tried to tell you in this story this evening is that there are a variety of ways that climate changes. And in order for us to have a conversation about climate change, we need to think about what time scale is appropriate for discussing climate change and what mechanisms are associated with those time scales. When we think about tectonically forced climate change, those are tens of millions of years, which is not a human time scale. That's not the time scale in which our economies and our lives operate. When we talk about changes in presence or absence of ice sheets, which have naturally occurred on our planet in the past, we're looking at changes in orbital variability as a forcing on tens of thousands to hundreds of thousands of years. Again, not really our time scale. But when we're looking at the last 150 years, those other time scales are relevant for contextualizing how out of normal our current rates of change in terms of temperatures really are. And that was the point that I wanted to get across to most of you today in this discussion, because I think it's very important for us to think about rates of change and the forcings which cause those climate changes. So with that, I've got time for questions, and I'm happy to expand on this discussion. Thank you very much. Please.
One quick question. I saw your chart about global temperatures. How were those measured in that year 1000 to year, I don't know, 1890?
Sure. This graphic of going back 1,000 years, this area that's the sort of white color right here, these are measured by thermometers.
Right.
This information here, note that the average is the red line, and you can see some background wiggles. Those represent errors because those are reconstructed temperatures using a variety of proxy data, such as tree rings. Like tree ring widths give us an indication of how warm or cool conditions were for given trees. Corals have similar sort of growth rings associated with them. We also have pollen data and pack rat data and ice core data. So, and I should say earlier, note that these error bars get smaller right about the 1600s. Most of this data is from shipping logs. And also from wine growing. Those wine growers, they keep very good track of temperature. So I have a friend who's a historical climatologist, and he scours through ship logs and people's diaries to reconstruct past temperatures. So that's why these are larger over here, because we have more error with the farther back in time we go.
So what does a ship log, I'm sorry, one last.
No.
What does a ship log have on it? Were they recording temperatures?
Yeah. Ships measure temperature, wind, sea surface temperature, cloudiness. Ship logs have all sorts of information.
You used thermometers in the 1860s or 70s.
Yeah, you know.
What are those?
I mean, I honestly, I have to say, I'm sorry to my colleague Carrie Mock that I don't know the answer to that particular question. Yeah.
It's really a global system of thermometers past that point.
Yeah, right. Past this point, the global thermometers, this information is very specific, similar types of thermometers, proofed and checked, cleared through the World Meteorological Organization, that sort of approach, yeah. Yes, in the back and then up front.
Can you go back a couple of slides to the energy balance?
Oh, yeah.
Okay.
Yeah.
There you go.
Yeah, energy balance.
Yeah. Energy coming in, absorbed by the surface. Does that include just thermal mass absorption, or does it include conversion of energy to food for plants?
No, we are just strictly talking about shortwave radiation that is making it to the surface.
So it's thermal mass.
Incoming solar radiation, yes.
Is there a significant amount that could be accounted by plants absorbing energy and converting it to food?
That's not part of this.
Energy can either be created or
yes, that's not part of this graphic. So here we're only talking about energy, shortwave coming in and longwave coming out. So we're not actually talking about any sort of biophysical process.
On the right, back radiation. Would that also include from clouds?
Yes, it would. In fact, that's what this top set represents, water vapor. Which water vapor, and you can see that water vapor operates a little bit over here on that short wavelength spectrum, as well as on the long wavelength spectrum. It turns out that clouds are some of the most difficult things to model in climate models because they both reflect incoming solar radiation, but they also absorb outgoing long wave radiation.
Is the data file for long-term cloudiness versus area on the surface of the Earth that could be applied to this?
Yeah, there are a whole bunch of different data sets. Again, ship logs tell us something about cloudiness. And since there are very specific shipping tracks across our oceans, we also have satellite data in terms of cloud data, and we have also superficial data in terms of cloud cover. But again, that's the tricky part, and that's where, let me get to this part. That's where some of this negative radiative forcings as it relates to aerosols are associated with, because some aerosols are associated with clouds and they have the ability to actually reflect incoming solar radiation, not as brightness, but as a function of the particulates that are in the clouds.
And on your analysis there, you were looking at global changes. Are you interested in any small area changes that might account for the difference in land elevation and the amount of atmosphere that energy has to go through?
Yeah, actually, I have to say there are a number of people at University of Wyoming in the Atmospheric Science Department that actually look at that very process, at those very processes, I should say, specifically in certain areas on our planet, like, for example, Southern California in some parts. There's a really interesting study in the days after the 9/11 attack, where there were no airplanes flying over North America. We actually had satellite data that gave us a huge snapshot into how much aerosols from contrails exist that lead to overall cooling of the surface of the planet because of the lack of air travel during the days after that event that led to the observation of how much energy was making it to the surface.
So the contrails were a net reduction of energy.
Yep.
Okay.
Yep. Yeah. Please.
Yeah, so if you, the slide, the little ice age,
Oh,
you can see very clearly when you go back.
Yeah, where do I want to go for the little ice age? Wait, I want to go here for the little ice age. Yeah.
Can you show us that and talk about the possible causes?
Oh boy. So this is a cooling for the little ice age. There are a couple of thoughts on this. One thought is that there were a couple of really good sizable volcanic eruptions. Krakatoa is a great example. Krakatoa erupted. It's in the tropical region because of atmospheric circulation and how large that eruption was. All this material got pushed up into the stratosphere and then circulated around the planet in both hemispheres, and it caused famine in Russia and in other parts of the world. It caused the summer without the year without a, thank you, the year without a summer, possible sort of nod to Mary Shelley and Lord Byron with their dark writings during that time period. That's one thought. Another interesting set of results that have come out of some analyses is that it is thought that some of the cooling that occurred during that little ice age is actually an after effect of depopulation that occurred in the New World. So we had a bunch of people that came into the New World and spread a whole bunch of disease and knocked out literally millions and millions of people because of diseases that they were not used to or not exposed to. Because of the rapid decline in population, much of the forests in Mesoamerica, in the New World, especially in Mesoamerica, rebounded. And as a result of those forests rebounding, CO2 was drawn out of the atmosphere with the photosynthetic process, and as a result, there was a cooling that occurred. So that's another potential driver of that little ice age cooling. There are other theories about little ice age cooling as it relates to ocean circulation and other things, so it could be one or many of those options. Good question. Thank you.
Yeah, as far as little ice age goes, Brian Lucky in Canada has done a lot of work.
Oh, yeah.
And it's very complicated. But as far as the Indians and disease, the little ice age started at least 100 years before it happened. So to me, that doesn't sound, I mean, it might have contributed to it.
Mm-hmm, exactly.
But as far as, I mean, maybe there's a lot more volcanic activity, but
exactly.
It's hard to find a smoking gun.
Exactly. I think it's likely a combination. Likely a combination of things, yeah. Please.
Yeah, your graphics are really fantastic.
Thank you.
Do you have a specialist who does that for you that you work with? You do it?
No, I do it all myself. Yep. I mean, when John was introducing me, one of my superpowers is geovisualization, and I do like clean graphics. My graduate students, it might drive them crazy. But it's very important if you're presenting information for it to be as clear as possible. And so I've worked on this quite a bit professionally. Actually, part of my dissertation actually had to do with color theory, believe it or not, because it had to do with making maps that the majority of people could view. So it really is about producing information that doesn't, leave out people who are, say, color deficient. 1 in 12 men, sorry guys, are color deficient, and they can't tell the difference between red and green. So using a rainbow color scheme on a map can be a dangerous thing because you lose a portion of your audience in terms of them understanding information. So yeah, that's one of my jams, so to speak. It is very time consuming, yes.
Do you have any opinions on, say, Eocene thermal maximum, how that might guide us on what's going to happen?
Yes, I guess my opinion would be it has to do with atmospheric chemistry. So I think that there's a huge connection there, that we can look at past periods when atmospheric chemistry was considerably different than it is today, or than it has been recent past, or even prior to those periods. That's probably the best I can go for the Eocene in terms of answering that question. I would rely on the same processes that I use to describe what's happening currently, and that relates to atmospheric chemistry and physics. Yeah, in the back.
I just had a question on your temperature and precip graphs.
Oh, uh-huh.
Where you compared temperatures to an average during the period 1951 to 80, or excuse me, 80 to 2010, I think, 30-year period temperatures, but for precip you used 51 to 80. Why not use long-term average to see what the...
So in this particular analysis, we use the long-term average, and for from a climatological perspective, from a climatology, 30 years is an acceptable long-term mean from average perspective. I think we use the same time frame for, oh sorry, this is stream flow. We use the same time frame for precipitation as we did for temperature in this particular study.
Yeah, this was all the way back when you look at global temperatures, I think.
Oh, okay.
Red and the blue bars.
Okay, so I think part of that has to do with, this is what I think I'm on the right track with answering your question here. Some of that data, some of the precipitation data, it also relies on satellite information, which really only became viable, say, since the late 1940s, early 1950s. Yeah. Right, exactly. Yeah.
Well,
so we use surface temperature. Yeah.
Why not use if you got data that goes from say 1910 to 2018? I would use long-term average.
Are you talking about this graphic here?
Yeah.
Yeah. So I'm almost certain that in in all of these graphics, where the zero line is representing, first of all, this is only temperature, yes, not precipitation, and the zero line represents 1981 to 2010. Right. Yeah.
Why not take into account the whole 1880
we could. We could, but as it turns out, it's not the standard of the World Meteorological Organization. The World Meteorological Organization standard is to take the most recent 30-year period to compare to. So actually, just recently, that 30-year average period has just shifted. Yeah.
For precip, you use to relate the older period.
Okay. Yeah.
That's what confused me.
Oh, because I'm using different data sources. So this is actually a data source through NCEI, Nestis, and NOAA. The precipitation data is actually climate division data, which went back to the 1950s for that particular station. And the reason I used 1950 for that particular study is because I was using a different data set for a different analysis that I don't even show you here for data that existed from 1949 to present. So it has to do with what we're analyzing and the time frames. So it's not a sleight of hand. First there's a question over here, and then we'll go over to the other side. Yeah?
Like what he said, if you had run out your average to those more years, what would happen there is that the line shift would change, so you wouldn't have any data below the line or above the line, depending on what.
Right, if you're averaging out the whole period.
To look at data like this, you'd like to see the crossing of the average.
Mm-hmm. Yeah, comparing it to that 30-year mean.
Yeah.
Yep.
And as long as you use the same one for all the graphs, you're okay.
Yep.
Trying to figure out how the zero line between 1951 and whatever it was, when absolutely everything is red and above zero.
Oh, huh?
I mean, you have a zero line, there's something below.
So anything that is close to the zero line means it's close to those average conditions of that long-term mean. Anything that below is cooler, anything above is warmer. What this is representing here in this portion, where it's a little bit above, a little bit below, a little bit above, you see that sort of fluctuation? That's probably just a function of the climate system adjusting or moving towards this new condition or this new state of what we see from a shift from variability or cooler. In fact, really what we're seeing here, this is some of that cooling that exists in the Cenozoic. That's a natural cooling process, right? We should be moving towards an ice age, but we are now not moving towards an ice age. And that's probably what this is representing, is that shift from a natural change in temperature to now a human-induced, whether you want to consider humans internal or external to the climate system. That's kind of a bigger meta discussion, I think. But I think this represents that transition that we're seeing. In other words, one thing to consider is that it takes time for gases to build up in the atmosphere since the Industrial Revolution. We can see the radiative forcing being relatively small around the 1950s, right? The radiative forcing increases moving closer and closer to present. So it basically is reflecting the overall change in the chemistry of the atmosphere from less greenhouse gases to now more and more greenhouse gases. And as we have more and more greenhouse gases, then we have an increase in the temperature, and the rate of the temperature increases more and more. And that's what we see from a bar graph perspective on that graphic that you're referring to. Does that make sense? It's pretty cool, except it's warming. So question over here and then in the back.
Yeah, can you go back to the red and blue bar graph?
Yeah, totally. You guys really love this.
And John, both their questions, I didn't quite get the answer for them. Is if your mean is from 1980 to 2010, that's what the mean is that you're using for the zero, you should have some blue in that way. And there's no way you can have every bar. So maybe this mean for these graphs is the whole period, not from 19
Could be.
to 2010.
Yeah, could be. Yeah. You know, you can actually, if you type in, it could be. That could be the case. Regardless, the trend is still the same. Yeah. Yeah.
It's true.
Yep.
That's right.
That's what was bothering me.
So there's a question in the back, and then we'll go up front. Please.
On a practical basis, say 2020 is about right now. In the next 20 years, what would you guess the number of degrees of temperature increase for our summers?
Oh.
I mean, with
This is good.
experience,
Yeah.
your charts,
Yeah. It's going to be warmer. There's about, let's see, I think in October, the New York Times ran a really interesting infographic article where you could type in your hometown and you can see how temperatures have increased since the year that you were born to present. And it also shows a projection of how temperatures are going to continue to increase over the next, I think they used a 50-year time period.
well, let's say I might live 20 years, I hope. In 20 years,
Yeah.
how much hotter degrees? Give me a degree number. 5 degrees warmer in 20 years? What would you guess?
I would guess in the next 20 years, we're probably going to see another degree C increase in temperature here in parts of Wyoming. 1 degree C, at least, in the next 20 years. This seems reasonable. You guys okay with that? Okay. I keep telling my husband, when we moved to Laramie, I said, don't worry, by the time we're ready to retire, we will be growing tomatoes in Laramie, and we do grow tomatoes now. So in the 15 years that we've lived in Laramie, summertime temperatures have increased enough that we can grow tomatoes. Now, granted, we're cheating because we add worm poop. Because if we were just to trust the soils in Laramie, there's not much nutrients in the soils for the tomatoes. So we're giving them a little edge, but temperature has increased over the last roughly 96 years in that part of the state by about almost 2.5 degrees C. So because the rate of change is increasing faster and faster, maybe invest in an air conditioner sometime in the future.
I've lived here 20 years, okay? And it seems like 20 years ago was a lot cooler. We had the first time in how many years it hardly got above 83 degrees.
Right.
83 degrees now is very, very often. It's
Yes.
cool. 83 degrees is pretty cool.
Yes, and in fact, that New York Times article, it actually identifies how many days of 90 degrees or more temperature your hometown will likely see moving forward in the future.
Well, what is it?
Well, I don't know. I have to. I'm not that good. I'm not that good. But when I moved to Laramie, I went to Ace Hardware and I heard some people talking about how they needed to buy an air conditioner. This was 15 years ago. How they needed to buy an air conditioner because it was 80 degrees. And I thought, coming from Arizona, oh my goodness, that's like February. So I understand what you're saying. It has increased faster, at a faster rate, over the last 10 to 20 years. So that faster rate is going to increase even more. That's why I'm guessing probably a degree.
More than 1 degree?
Well, 1 degree C, right? 1 degree Celsius, yeah. And that's on average. So so you're likely to see some 90 degree temperatures. Sorry if you don't want to get warm. It'll happen. Please.
My question is about all the droughts and stuff and the water conditions and all the different things that you said are going to affect the amount of water. and we're having more and more and more people in this world. And like it said, less water and more people. Are you involved in any of the people that make decisions for water on the west here?
You know, interestingly enough, so I work with a couple of different groups. One group that I'm working with is actually working on a study in the Green River Basin to identify how people view drought, how they perceive it, and with some examples moving forward of, you know, high, medium, or low likelihood of drought in the future, what their viewpoints are of that. This is where your question really lies very squarely in a realm that most of us scientists don't work on. Because where we're moving in the future is less about what's going to happen when it gets warm, because it's going to get warm. I guarantee you it's going to get warm. How much by how many degrees? More. Okay? But what do we do about it is the domain largely of social scientists. And that's where things get trickier. I mean, I talk about this quite a bit as this is our moonshot. This is where we're moving in the future. It turns out that chemistry and physics don't care about politics. They don't care about state lines. They don't care about impoundments. Increases in temperature are moving forward. What is going to happen from a water resource perspective is causing these folks to freak out, because this is our single fastest growing population in the United States is the Southwest. In a very unsustainable situation that is relying on water from these locations in our backyards that is becoming less and less, even though there's variability. Like, it's a really wet year this year. Is it enough of a wet year to make a difference at this dam right here in Lake Mead for a long time period? That's the tougher question. And what do we do, if anything, do we do about it? That involves questions of politics, state lines, economics, ethics, religion, people's belief systems. Those are not within the domain of chemistry and physics, and it's considerably trickier. And you've just identified the real big question.
When does it get to a tipping point where people stop worrying so much about this and get invested in desalination?
Oh man, you ask a question that every year somebody asks in one of my classes. Desalination is real and is going on right here in Yuma, Arizona, because we're required by law to provide Mexico with a certain amount of water, because the end point of this river used to be down here in Mexico, but the river doesn't make it down there anymore. So Yuma takes all this agricultural water, takes all the toxins out and all the salts out, desalinates it, and sends fresh water down to Mexico. At our expense, because we are required. And the cost for desalination is very high because it takes, guess what? A ton of energy to take salt out of water.
Take that. You already produced electric power.
Yeah.
You take the cycle of that, or change nukes.
Yeah, it's true. And what's interesting about this is, in terms of thinking about energy and water, this is a really interesting graphic from Scientific America. How many megawatt hours are required for desalination of salt water or seawater, right? The energy that it takes to desalinate water is pretty high, and what energy is used is, at this point, is largely coal or natural gas based. So any energy that's being used to desalinate water is also being used to warm the planet as well. Irony. Yeah.
Okay, I apologize, but we're really short on time and cleaning up the room. So, JJ, thank you.
Thank you very much for the questions. Thanks to all of you.
As a red-green blind person, I didn't struggle.